Hello class, welcome to this video on the geometry midterm review. So there are about 60 questions on here, so I'm going to break this up into a three-part series. So let's go ahead and cover the first 20 questions in the review. So number one says, given A is parallel to C and B is parallel to C, draw a conclusion about A and B. Well, if we know that A is parallel to C and B is parallel to C, well then that implies that A is parallel to C, right? So, and that's by the transitive property. Remember, the transitive property states that if A equals B, B equals C, then A equals C. Well, this is the same idea. If A is parallel to B and B is parallel to C, then A is parallel to C. Okay, so A and B are parallel because if two, in this case, if two parallel lines, or if two lines are parallel to the same line, then they are parallel to each other. And that's essentially the transitive property. All right, number two, points L, M, and N are collinear. You're given LM equals 7 and LN equals 12. What is the value of MN? Okay, so we're going to draw a number line here. So collinear means that these 3 points are on the same line. So that means that they're located on the same line, and in this case I'll just draw a number line. Now it says LM, the distance from L to M is equal to 7, and from L to N is equal to 12. So we have here the distance from L to M is 7. The distance from L to N is 12, like this. And so you can clearly see, once you draw this out, well, you can kind of tell, okay, well, then that means that M to N has to be 5, since 5 plus 7 is 12. And this is the segment addition postulate, which states that, you know, if you sum two line segments together, in this case LM plus MN is equal to LN, and that's your segment addition postulate. And so in this case we have 7 plus X equals 12, so the unknown has to be 5. Okay, so we got our answer, it's going to be equal to 5. Number three, the angle bisector of angle ABC is ray BP. If the measure of angle ABP is 6n, what is the measure of angle ABC? So we have an angle labeled ABC, so that's ray BA, and this is ray BC. And so this makes angle ABC, and this is in that order. In this case, B is the vertex. Now there's an angle bisector. Bisector means you cut something in half. So this is something that's cutting this angle right here, this angle in half. So the bisector is BP, so there's some kind of P here such that this is a ray. Okay, so that's cutting this angle in half. And so this angle is equal to this angle on the other side. So then it says ABP is 6n. So that means that if this is 6n, then that means below here has to be 6n as well, right? So we know what that is. So in this case, ABC is 6n plus 6n, which is equal to 12n. So the measure of angle ABC is 12n degrees. Pretty straightforward. There's no numerical answer for it. It's just going to be a variable answer. All right, number four, given xy and zw intersect at point A, which conjecture is always true about the given statement? So let's go ahead and draw some lines here for xy. Remember, a line requires 2 points, so those points in this case are xy, and line zw. And they said they intersect at A. So let's call this line ZW, okay? Now this is just one of many pictures. You can draw many different pictures from many different diagrams from this description here. And so it's saying which conjecture is always true. So is it always true that XA is equal to AY? So is it always true that this distance is the same as that distance? Well, no, in this case it looks like they're the same, but they could have easily been far apart, right? So for example, I could have easily put point Y over here, for instance, and then those distances will no longer be the same. Okay, so it doesn't matter where X and Y are, this is still gonna be line XY, all right? So this is not gonna be true. Angle XAZ is acute. Angle XAZ, in this case acute, remember acute angle is less than 90 degrees. And this looks kind of like it's a little bit less than 90 degrees, really not too far from 90 degrees. But this does not necessarily have to be true. I could easily have drawn this so that it's still gonna be XY, and I could have drawn the line this way, right? And that's still gonna be the line ZW if I move the points. And this is gonna be an obtuse angle in that case. So this is not necessarily gonna be true. XY is perpendicular to ZW. So in this case, they're saying that these cross at a right angle. Again, that's not necessarily going to be true. Like in this diagram here, it's an obtuse angle and it's not a right angle. So this is not true. Remember, perpendicular means that they cross at a 90-degree angle. All right, and then the last coordinate, X, Y, Z, and W are non-collinear. This is true of any diagram. In both of these diagrams, X, Y, Z, W are on different lines. And so therefore they are by definition non-collinear. So this is true. Number 5, point F prime is the image when point F is reflected over the line x equals -2 and then over the line y equals 3. The location of F prime is 3, 7. What is the location of point F? So here we have, let's go ahead and write let's go ahead and draw the location of point F here. Now it helps to kind of draw this out. So point F here is 3, or F prime rather. It's going to be 3, -7. Now so this is the final product after we have reflected by x equals -2 and then y equals 3. And so what we want to do is we want to reverse this process, right? We want to instead reverse it and go over y equals 3 and then go over x equals -2. So if we reverse this process, then let's go ahead and reflect backwards again over y equals 3. So y equals 3 is a horizontal line. Remember, y equals is horizontal, x equals is vertical. So let's go reflect over y equals 3 here. And remember, a reflection is simply moving over on the, flipping over on the other side at the same distance. So the distance from this -7 to this 3, this is a distance of 10, and so I got to reflect it 10 on the other side. So let's go ahead and count this out. So here we have 10, and so here we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll go ahead and extend my number line just to give myself some more room. And so this is going to be F before it got reflected across y equals -3 or y equals 3. Now let's go ahead and reflect this over, and the coordinates of this, by the way, let's go ahead and write the coordinates: 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now we're going to reflect it over x equals -2. Let's draw that. -2 is over here, and it's going to be vertical. So this is x equals -2, this vertical line. Let's reflect it over that line. Okay, so the distance from this horizontal line to this F is 1, 2, 3, 4, 5. The distance between 3 and -2, which is 5. So we're going to move it 5 to the left. 5 over here, and then put it at the same level as this F here. Okay, And that right there is where f was originally. I'm just going to call this f double prime because I don't have any other designation. So this is my original f. And then now let's see if it works. Going across -2 takes us here. And then across 3 takes us there. And so the original coordinate of f is, according to this, we have -3, -7 here, and 13. So those are my final coordinates. All right, number 6, what are the coordinates of B prime after the pentagon is reflected across the x-axis and then rotated 90 degrees about the origin? Okay, so we have here a pentagon in the diagram, and we're interested in B. So let's go ahead and do what it says, which is to reflect it across the x. So if we want to reflect this across the x-axis, we want to reflect across this axis here, kind of like what we did earlier. We're going to flip it across. So the distance here is 1, 2, 3, 4, 5, and so it has to be the same distance, 1, 2, 3, 4, 5. That's going to be right there. So that's a reflection. We'll call it double prime until it gets to 1 prime here. And then now we're going to rotate it 90 degrees about the origin. So if we want to rotate it, we're going to rotate it from here. And there's a rule for rotating about the origin, and I'll go ahead and list the rule. So if you have a coordinate, say xy, and you want to rotate this coordinate, let's go ahead and draw it over here like this. So let's say we have a coordinate 2, 1, for example, and I want to rotate this 90 degrees. Well, if I want to rotate 90 degrees is, by the way, a positive value, which means you're doing this counterclockwise. If it was -90 degrees, you would be doing it clockwise. So we're rotating it counterclockwise by 90 degrees at a right angle. And so it'll look something like this. So it'll go at, here, let me go ahead and draw this a little bit better. So it'll look something like that. This will be rotated 90 degrees, and then the new coordinates will be -1 and 2. So the rule for rotation about the origin 90 degrees, and this is the symbol that I use for that, rotation about the origin 90 degrees of the coordinate xy. The rule for that is that you switch the x and the y values, because this is going to be -1, 2. So you switch the x and the y values. So now y is x, x is y. And then you take the opposite of the y value, which is now going to be the new x value right here. So this is the rule. And you can also write this in arrow notation like this. This is a rotation 90 degrees. Counterclockwise. Okay, so now that we got the rule down, we can go ahead and use the rule here. So we know that the coordinates of B double prime are 1, and let's see, 1, 2, 3, 4, 5. So 1, -5. And so this is x, this is y. So if I put this into that transformation, let's go ahead and using that rule. So 1, -5, let's do a rotation. Then you're going to switch the x and the y together. So it's going to be -5, 1, and then you're going to negate the y value. So right now the y value is 5, so now it's going to be negated and be +5. So you switch the sign. This doesn't necessarily mean that there's a negative sign. This just means that you're going to take the opposite of that value, and the opposite of -5 is 5. So this is going to be my new coordinate. Okay, so then that means B prime is going to be 1, 2, 3, 4, 5, and it's going to be right over here. This is going to be where B prime is, 5, 1. And you can see that if I take this and I rotate it counterclockwise 90 degrees, it indeed gives me that this is a right angle. So those are my new coordinates, going to be 5 and 1. All right. Let's do number 7. So what are the coordinates of E prime after the pentagon is rotated 270 degrees about the origin and then reflected across the y-axis? Okay, so we just went over that the rule for rotation about the origin of 90 degrees of a given coordinate is negative y and x. Now let's look at the rule for rotation about the origin 270 degrees counterclockwise of any given coordinate. So what's the rule for that? Okay, so if I have a coordinate, say the same, let's use the same coordinate, 2, 1. And I want to rotate it. Well, if I want to rotate it 90 degrees, I go over here, which is, we know that's going to be -1 or -1, 2. Then if I rotate that another 90 degrees, then that brings me down to -2, -1. And then that's 180 degrees. Now we're going to go 270, right? So 270 is going to be going over here. And in that case, okay, so in this case, you'll be like over here. And then if you notice, these coordinates are going to be 1, -2. So essentially what happens is you flip x and y again, and then looks like the x value is changed to negative sign. So in this case, the rule is you switch y and x just like you did before, but now this is going to be negative. Okay, so that's the rule for 270 degrees counterclockwise. And remember that the rule for rotation is that when you rotate across, the distance here has to be the same throughout. So notice that I tried to make sure that the distances stayed the same, more or less the same as I rotated. So this could not have been rotated, for example, here, because that would have been, well, first off, it wouldn't have been 90 degrees. So, so that would be incorrect because this is not a 90-degree rotation. So I was trying to make it so it's a right angle, but at the same time, make sure that the distance is the same as well, okay? So in any case, we got the rule for rotation, so let's use it. So the coordinates of E prime after it's rotated 270. So now we're gonna take this, it's rotated 270. This is, the coordinates of this are 1, or 2 rather, 1, 2, and then 1. So 2, 1. Let's put it through the transformation. So 2, 1 transforms to, using a 270 rule. You switch x and y, just like we did here in this rule, and then the x coordinate, that the second coordinate becomes the opposite. So you're just going to put a negative there. So that's my coordinate, 1, -2. So that's where we're at for a rotation. So we're at 1, -2. We'll call this double prime. Now to make it into a prime, I will reflect it across the y-axis. So the reflection across the y-axis, remember that this is the y-axis here. And so I'm going to reflect it across that on the opposite side, like over here. And that will be E prime. So the coordinates of that are -1 and 1, 2, -2. So the coordinates there, -1, -2. I guess I should put it here for the response. All right, and that takes care of that question. Triangle JKL is reflected across x equals 0 and then translated 5 units up to create triangle J prime, K prime, L prime. Are the two figures congruent? So if triangle JKA is being reflected and then translated, so notice that reflections and translations do nothing to the shape of the object. They simply move the object around. So if I have any triangle, let's say I have a right triangle and I move it around in space, it stays a right triangle. It doesn't get bigger or smaller. And if I reflect it, it does the same thing. It doesn't change size all of a sudden magically, right? So these are known as rigid motions. Remember, there are several transformations that we call rigid motions, or sometimes they refer to them as isometries. And in this case, they don't change the lengths of the figure, and they don't change the angles of the figure. They maintain the rigidity of the figure. And those are rotations, reflections, translations, and any combination thereof, including, but not limited to, what we call glide reflections. There's other, which this is just a combination of reflections and translations. So basically anything that transforms it but does not change the size of the shape or the angles is a rigid motion, and that means that the two figures will be congruent. These are also known as congruence transformations because they leave the figure intact and they don't change the size in any way, and so therefore they're congruent. So the answer is yes, the reflections and translations preserve lengths and angle measures, so the figures are congruent. Number 9, what is the least angle of rotation that maps the regular heptagon onto itself? Round your answer to the nearest whole degree. All right, so we're talking about rotational symmetry here. So rotational symmetry about the center here. So this figure does indeed have rotational symmetry, which means to say that I can take, for instance, this part of the figure and I can transform it so that if I rotate it, it becomes the same figure. So if I rotate it from this sector to this sector, then you can kind of see that they're going to overlap, and you won't be able to tell the difference in the figure, in the shapes. They're overlapping. Okay, so therefore, how do I figure out that angle? Well, to figure out that angle, we know that since it's a heptagon, there are 7 sectors in there. There's 7 sides, and therefore 7 sectors. And so we know that if we do a full 360 degree motion, then we'll go back to where we started. So if we do 360 degrees divided by 7 rotations of these sectors, then we'll get the number of degrees that are required for each of these sectors. Okay, so if we divide those together, we get about 51 degrees. So we'll go ahead and round it to the nearest whole degree. So if I rotate these about 51 degrees from here to here and so on, then the shape will overlap with itself. And so we could say that the angle of rotational symmetry is 51 degrees, around there. What is the minimum angle in degrees that any rectangle that is not a square should be rotated about its center so that the rectangle maps onto itself? So if you have a rectangle that's not a square and you want to rotate it about its center, so you want to take this point and rotate it, you want to take this point and rotate it, all the points in the rectangle, but let's say we focus on these 2 points. If I rotate them 90 degrees, then the rectangle kind of goes up like that. And this will represent a 90 degree rotation. And then if I do another 90 degrees, then this red point will go down here. Or rather, it would go, I did the wrong color here. This one's going to be the black one. This one's going to be the red one. Apologize for that. Let me redraw this rectangle. Okay, so now this red one will go up here because this will rotate 90 degrees this way, and then this will rotate 90 degrees this way. And so you'll end up, if you rotate 90 degrees, then you'll get something like that, where the black one goes down here, this red one goes over here. So, and you can see that they overlap. So now the rectangles will only overlap if you rotate it 180 degrees minimum. Okay, so every 180 degrees, then you're fine. Which regular polygon has a minimum rotation of 45 degrees to carry the polygon onto itself? So remember that for the heptagon, the minimum rotation was 51 degrees, and that depended on the number of sides. So the formula for the angle of rotation is 360 degrees divided by the order. We call this the order. So if we divide it by some order, then, which is essentially the number of sides in this example, and this has to be 45 degrees. So this is our equation, 365 divided by the number of sides is equal to 45. And then we can solve this equation very easily. So what we do is we multiply by n to cancel it out because it's dividing here. So we had 360 equals 45n, then divide by 45, and that will get n by itself on one side. So all we have to do is 360 divided by 45, and that will tell us how many sides we have in our polygon, which is going to be equal to 8. So if we're dealing with a polygon with 8 sides, then that's an octagon. Which transformation will place the trapezoid onto itself? So this is the trapezoid of the problem. So let's do a counterclockwise rotation about the origin by 90 degrees. Is that going to map this onto itself? That is to say, will it overlap when I do this? So we're doing it about the origin. So if we take this and we, project a line onto that point from here to here, we rotate that 90 degrees. 90 degrees is about an L, right? That's a 90-degree angle. And so I'm going to kind of estimate this here. But if I were to do this 90 degrees, well then it'll probably look something like that, right? This is a 90-degree angle and we're doing it counterclockwise. So it'll probably look something like this. And you can see that if I did that, this is not overlapping with any points, right? And so therefore this is not even going to work. But I'm going to draw the picture of this trapezoid so you can kind of see how it would look like. Now remember that the rule for 90-degree rotation is xy transforms to negative yx. And so we really could use this rule to help us out here. So let's do that. If we switch 3 and 2, we get if we switch these coordinates, we get 3 and 2, and so we'll end up getting negative 3 and 2, which is going to be over here. And then if we transform this point here, which I'll mark for green, then we're going to get negative 3, negative 2. Right there. I'll mark this in purple. So that's going to be positive 3, negative 4. That'll be around here. And then this coordinate, which was at 4, negative 3, will transform into 3, 4. So you can kind of see that if I did that rotation, it would look like that. And that definitely does not look like the original shape. So definitely not a counterclockwise rotation about 90 degrees. Now, if I did a rotation by 180 degrees, what's going to happen? Well, I'm going to do this again, right? I could do another 90-degree rotation. And if I did that, then you can kind of see that this right here will kind of go over here, and you'll have something that kind of looks like that, which is definitely not overlapping. And I'll go ahead and show you by using the rule. The rule for rotation about 180 degrees is negative x, negative y. So if we did that, we get negative 2, negative 3, which is over here, positive 2, negative 3. This is going to be negative 4, positive 3, or yeah, negative 4, positive 3. And then this one over here, which is exactly what I said it would look like, something like this. So definitely not A, definitely not B. So let's do another rule. Reflection across the x-axis. So that means we're reflecting across this line here. If I do that, well, then this is going to map over here on this side, right? And this is going to map over on this side. This is going to map over on this side and that side, which looks similar to the rotation 180. So this is not correct. All right, and then lastly, reflection across the y-axis. If this is the y-axis, let's do this in blue. If I reflect this, this is going to go here, this is going to go here, and therefore they overlap. So that is correct. All right, number 13, the line segment AB is shown below. Which transformation of AB will produce a line segment A prime B prime that is parallel to the original AB? Rotation 180 degrees about point P. So let's go ahead and do that. We want to rotate about point P. So that means we want to rotate 180 degrees. So this way, if we did that, then we get a line that looks kind of like this. And that is not parallel to that line, so that is not correct. It's actually on top of that line if you were to extend it. So this is not true. Now, if you rotate 90 degrees counterclockwise, which means this way, then it's going to be rotated so it makes an L with the original shape. So something like this, that looks like a 90-degree angle. It'll rotate, it'll look like this. So this is actually going to be a 90-degree angle, and that's perpendicular, not parallel. So this is not correct. That would be perpendicular in that case. Reflection over the x-axis. So this is the x-axis here. If we reflect that, this is, let's see here, this is 2 units away here, 2 units away here. It'll go like there. This is 1, 2, 3, 4, 5, 6 units away. 5, 6 units away. So if you reflect it, it'll look something like that. If you were to reflect them about that, those are clearly not parallel. So that's not correct. And then finally, translation down 2 units. That just means that you're moving these down 2, moving this down 2, and that's going to be your line. And those are indeed parallel. They'll never cross. And so therefore, the answer is a translation. Number 14, a line segment AB is drawn in the first quadrant. Its image, line segment A prime B prime, is formed by reflecting AB over the x-axis. Which statement will always be true? So that key word there. So line segments AB and A prime B prime are parallel to each other. Will that be true? So if I were to draw, and it says in the first quadrant, so that's this quadrant right here. So if I were to draw some line segment AB and I were to reflect it over the x, so this reflected over this axis here. So they'll only be parallel to each other if I have a line segment like this. If I have a line segment like that, then in our reflected, then it's going to look like that. So that's only true if this line segment is horizontal, but it's not true if, for example, we had something like this, right? We said earlier in the previous example, it'll look kind of like this if you reflect it like a mirror image. So this is not parallel. So this is not always true. So it's not A. Will they be perpendicular to each other? Well, clearly, if I reflected this, this is not perpendicular, so that eliminates that answer as well. When will they be perpendicular? Well, there's not really a case where you can get them to be perpendicular. Well, actually, there is. And that case would be if, for example, you have a 45-degree angle here, and then when you reflect it, you get another 45-degree angle on the other side. And that, in that case, that would be perpendicular. So that's the only way that you can get them to be perpendicular in that case. But that's not always, so it's not true. Corresponding points on AB and A prime B prime are equidistant from the x-axis. And that is true. It doesn't matter what line segment you draw. The purpose of the reflection is to flip it over in the same distance as what it is on the other side. And so they're equidistant from the x-axis. That is true. Just to analyze all the questions, let's look at D. Corresponding points can be connected to form line segments perpendicular to the both. And that is not true. If you look at this one, if I connect this line segment to that point, that does not make a 90-degree angle. That's an acute angle. So that's not true. All right, so the answer is C. All right, number 15. A person facing east walks east 20 paces, turns, walks north 10 paces, walks west 25 paces, then south, then walks east 15 paces, and so on. So this looks like this person is going all over the place. So we have here east 20 paces. Let's say let's make the markers that are 10 each. since that seems to suit the problem very well. So we have someone facing east. So this is east, north, west, south. So if we're going east 20 paces, then you're over here. And then he walks north 10 paces. So this is point position 1, position 2. Then he walks west 25 paces. So that's 10, 20, 25 is around here, halfway. And then he walks south 10 paces. So that means he's down here. Position 4. And then he walks east 15 paces. So that's 5 and then 15. So basically you're over here. So somewhere over there. And so really what the person could have done, instead of done all this circle about route, he could have just, in this case, he could have just gone from the origin over 10, and he would have ended up in the same spot. And therefore, the only way that he can get to the same spot is by doing a translation, a different type of translation, a different amount of units, just going a translation 10 east. Number 16, point P prime 5, negative 4 is the image of P, which is 2, 3 under a translation. What is the image of 6, negative 2 under the same translation? So P prime is the image, so you're going from 2, 3 to 5, negative 4. Remember, the pre-image is what you start out with. The image is the aftermath of the transformation. So how much are we going from 2 to 5 if we're doing a translation? Well, clearly it looks like we're going, according to the x coordinates, we're going 3 to the right, which is to say we're going plus 3 in the positive direction. And for the y direction, from 3 to negative 4, looks like we're going down 7. And we can tell because 3, negative 4 minus 3 is negative 7. And 5 minus 2 is 3. So all we got to do is go 3 to the right, down 7. So the transformation rule that we're looking at here is x plus 3 and y minus 7. So that's my transformation rule. Now we can take any coordinate and use that transformation rule, and we'll be fine. So it says, what is the image of 6, negative 2 under that same transformation? All right, so we got 6 plus 3, negative 2 minus 7. So you're just moving it 3 to the right and 7 down, and this is going to be your new, the image of that transformation. All right, so number 17, triangle ABC is translated to form another triangle A prime, B prime, C prime as shown in the coordinate plane. What are the translations applied to triangle ABC to form A prime, B prime, C prime? So this should actually say transformations rather than translations. A transformation can be any, a translation is a type of transformation. So it could be, and a transformation is just a generic change from pre-image to image. So let's look at each of these to see which one's the right answer. Let's do a reflection across the y-axis. So this is the pre-image here, and then the primes are the image. So if we were to reflect this, say about the y-axis, then we're reflecting here. This will be that's 2 units this way, so it's going to be 2 units this way. Right off the bat, we can see that they don't overlap, so this is not the right transformation. Reflection 180 degrees about the origin. So reflection, or rotation rather, about the origin. So the coordinates here are negative 2 and 3. That's negative 2 and that's a 3. And so if I were to rotate it, it would go on the other side like this, and we can see that that's definitely not going to overlap with this. So that is not true. It's not going to be rotated 180 degrees. Right 6 and up 1. So 1, 2, 3, 4, 5, 6, and then up 1, that is true. 1, 2, 3, 4, 5, 6, up 1, that is true. Yes, so all of them can be moved 6 to the right and 1 up. So that's my transformation. Which transformation maps the solid figure onto the dashed figure? Okay, so let's look at the rotation 180 degrees about the origin. Let's see if that works. So I'm going to take this coordinate here about the origin. I'm going to rotate it 180 degrees. And that looks like at the same distance, right? These are the same distance, and 180 degrees, which is half of a circle, and that takes me there. If I take this and I do another half circle right there, that'll take me to that point. This looks good so far. Let's do the other 2 points, and I'll erase these two so we have a good reference. From here to the origin, rotate that 180 degrees. Same distance takes me there. Last point here, distance from the origin, rotated 180 degrees, and we're given this coordinate here. So that is true. This is a rotation 180 degrees about the origin. Select all the rotations about point P that carry the regular decagon onto itself. So this is another rotational symmetry problem. So if I were to take this, and how much will I need to rotate it to get there? Well, since it's a decagon, there are 10 sectors that can be, 10 congruent sectors that can be drawn here of this size. And so the angle of rotation is 360 over 10, which is 36. So that is to say, I can rotate this 36 degrees or any integer multiple thereof, and that will have me map the figure onto itself. So I can rotate it 36 degrees, I can rotate it 36 degrees twice, or 72 degrees. I can do it 3 times. In that case, that'll give me an angle of 108 degrees, which we do have here, that is true. I can do it 1 more time and give me 144 degrees, and so on, and that is true. And those are my only angles that I can rotate for this problem. All right, last problem. What trapezoid WXYZ is shown below? What series of reflections will map the image back onto the original pre-image? Okay, so this is our trapezoid. So if we reflect about x-axis, so let's go ahead and do that. So reflect about the x-axis first. So we got 1, 2, 3 units there. So it's going to be 3 units here. That's going to be W prime. We'll just call it W prime. And then 1, 2, 3. This is 1, 2, 3, 4, 5, 6, 7, about 7. And that's Y. And this is about 7 as well. So this is going to be a reflection about the x-axis. That's done. Now let's do the y-axis. So we're going to reflect it this way. That's 3 units this way, 3 units that way, 4, 5, 6, 7, 8 units that way. YZ. And then this is 1, 2, 3, 4 units that way. This will be W. And that's 7 units that way. So this is a reflection about the y-axis. And now let's do a reflection about the x-axis again. So this is going to go back here, or let me make sure I did this correctly. 1, 2, 3. Okay, so 1, 2, 3, 1, 2, 3. It's going to go back. It's going to basically look the same on the other side. So it's going to look like this again. So that's another x-axis, and then we're going to do another y-axis again. So you can kind of see it'll map onto the same direction as well. So this is W. I forgot to label this. This is X, Y, and Z. And you can see that it'll overlap with itself if you flip it. So this is the correct response. Okay, that's going to be it for the first part. I'll go ahead and finish the other part in another video. Thank you guys. I hope you found this useful. As usual, I'll see you in the next one.